Alright, time for the last video. This one is on light, sound, and wave interactions. Things like refraction, reflection, diffraction, and interference. Let's start off by talking about what light is. Light is a form of electromagnetic radiation that we can see. There's an entire spectrum of electromagnetic radiation. Light, right about in the middle. This is the part of it we can see. Everything else is invisible to us. It includes radio waves, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. You need to know this spectrum in order. You need to know what order it's in. As we can see from the illustration here, it is going from long wavelength to short wavelength. Wavelengths down in radio waves are about the length of football fields. The wavelengths up here in gamma rays, well, they're about the size of the nucleus of an atom. So this is from long wavelength to short wavelength. You also need to know it in terms of frequency. The frequency down here is 10 to the 4th hertz. That's low frequency as far as the electromagnetic spectrum is concerned. All the way up to 10 to the 20th hertz. Very, very, very high frequency. So again, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray, long wavelength to short wavelength, low frequency to high frequency. Do remember these things are related to energy. Long wavelength, low frequency means low energy. So radio wave is the lowest energy form. Gamma ray, short wavelength, very, very high frequency, very, very high energy. So this is also low energy to high energy. In fact, when you get to ultraviolet, beyond the energy up here is dangerous amounts of energy. All of these can cause damage to our body. All of these can cause cancer. They carry so much energy. Down here, these are lower, so they're less likely to cause us harm. There's some things you need to know about light. It is a transverse wave. Those are the perpendicular ones. They are vibrations in electric and magnetic fields. We're not vibrating matter this time. We're vibrating electric and magnetic fields. And it goes like that. The fields vibrate like this, while the wave moves like that. 90-degree angle. Perpendicular, transverse wave. The big thing is, since it is a vibration, electric and magnetic fields, it can travel through a vacuum. It can travel through the emptiness of space. It is the only type of wave that can do that. Sound. Let's talk about what it is. Sound is a form of mechanical energy that travels as a wave. Remember, mechanical energy involves moving objects, taking objects out of their resting position. What makes sound different from regular mechanical energy is that in the regular mechanical energy, we're moving the whole object from one place to another. In sound, we're just producing a vibration in that object. The object really doesn't go anywhere, but the vibration moves through it. With sound, my vocal cords vibrate the air as they pass through it. And that vibration then vibrates the air outside of my head. That vibration then travels from me to the video camera, from the speakers on your computer to your ears. It's a vibration that's traveling through the ear. It enters our ear canal, vibrates our eardrum and the bones of the inner ear, vibrates the cochlea, which has nerve cells in it that pick up that vibration, turn it into electrical signals that go to our brain. Things you need to know about sound. Sound does require a medium. Sound cannot travel through the emptiness of space. It has to have matter. One of my pet peeves about science fiction movies is when you're watching that big space battle like in Star Wars, you can see the whole thing happen, but if you want to know what it's really like, hit the mute button, because you wouldn't hear anything at all. There's no air in space, there's no medium in space to carry those sound waves. So the spaceship would blow up over there, you'd see a big explosion, but you wouldn't hear a thing. Pitch is our perception of frequency. Again, how many waves hit you per second. High frequency means a lot of waves every second. We perceive that as high pitch. Those are the treble sounds, flutes, violins. Low frequency, long wavelengths, we don't get hit by them very often. We perceive that as low pitch or bass. Things like bass guitars, bass drums. Loudness is our perception of amplitude. How much energy the wave carries. High amplitude, loud sounds. Small amplitude, quiet sounds. This is why loud sounds can damage our ears. High amplitude waves carry a lot of energy. A lot of energy can cause a lot of damage. Which is why we need to make sure that when we listen to iPods and things like that, we keep the volumes at reasonable levels so we're not channeling too much energy down our ears. As far as interactions go, interference, reflection, refraction, and diffraction. Interference is how they interact with each other. The last three are how they interact with barriers. Basically, reflection being bouncing. As the wave hits the barrier, it bounces off. Refraction and diffraction both involve bending, but bending in two different circumstances. Refraction, bending as it goes into another medium. Diffraction is bending as it passes the edge of a barrier. We're going to see that in just a second. Let's start with the interference. In interference, what we have are two waves colliding. Constructive interference is when they collide in phase. In other words, the crest of one wave hits the crest of another. The trough of one wave hits the trough of another. Constructive interference occurs when they collide in phase, or the same parts collide. When that happens, we have one wave trying to pull up on the medium. We have the other wave trying to pull up on the medium. They are working together. The net result, we pull the medium further. We take the amplitudes from both waves and we add them together. Constructive interference is additive. We add the amplitude. The net result is we get a single larger wave. So if these are two speakers producing sounds, we end up with a single louder sound. If these are two lights producing waves, we end up with a single brighter light. Constructive interference, additive, combine the waves together, make a bigger wave. The other type of interference is called destructive. They meet out of phase. The crest on one wave meets the trough on another. The crest on one wave meets the trough on another. And what we have here is the exact opposite situation. This wave's trying to pull up, this wave's trying to pull down. It's like tug of war, and the medium doesn't go anywhere. We end up taking the amplitude from this wave, subtracting the amplitude from this wave. They cancel out, there is no wave. This is the way noise-canceling headphones work. There's outside sound. The headphones produce an out-of-phase sound inside the speakers to cancel it out. If these are two speakers working against each other, you cancel out the sound. If these are two lights working against each other, it cancels out the light and ends up being dark. Constructive interference will make things louder and brighter. Destructive interference will make things darker and quieter. As far as the barriers go, reflection is the bouncing of waves. Again, the wave comes in, hits the barrier, bounces off. It's governed by the law of reflection that tells us that the angle at which it hits the surface will be the same as the angle at which it leaves the surface. This dashed line here is an imaginary line called the normal. It's perpendicular to our surface. If we measure, again, the angle at which it hits the surface, called the angle of incidence, it will be equal to the angle at which it leaves the surface, called angle of reflection. If you ever shot pool, you know this. You try to make a bank shot, the angle that it hits the bumper will be the same as the angle that it leaves the bumper. If you ever played basketball, you know this. The angle that it hits the backboard will be the same as the angle that it leaves the backboard. Works for light and sound as well. We use mirrors as a source of reflection to see ourselves. The light leaves our body, hits the mirror, bounces back. It's reflection. Echoes are a reflection of sound. Refraction. This time, instead of bouncing off the barrier, and this is our barrier, this is our surface right here, instead of bouncing off that surface, we go through that surface. We go from one medium to another. And if there's a different density from one medium to the next, so let's say this is low density up here, high density down here. As it goes from low density to high density, that's actually going to change the speed of the wave. It's going to slow it down. In the case of light, when light goes from low density to high density, it will actually slow that light wave down. And as it slows down, it actually bends the wave. In this case, you see it bent it towards this imaginary line called the normal. It bends the light, it changes its direction as it goes from one medium to the next. If you ever stuck a pencil in a glass of water and that pencil looks bent or broken, this is why. The light is being bent by the water in the glass. This is the same technology that lenses use. There are two types of lenses. There's the convex lens that curves outward. There's the concave lens, it curves inward. And the way lenses work is they bend light towards the thickest part. So in this one, it would bend light this direction towards the center, because that's the thickest part. In this lens, it would bend the light this way, out and away from the center, because the thicker parts are out and away from the center. Lenses bend light from, or using refraction, as we go from low density to high density. Low density to high density. It bends the light. This is what we use in glasses, telescopes, microscopes, anything with lenses in it, camera lenses, etc. Diffraction is the last one. Diffraction is the bending of light again, but this time as it passes the edge of a barrier. Here we have a picture of a bay on the ocean. You can see the land jets out and creates a small opening. As the waves approach, they're approaching in nice straight lines. But as they go through, those waves get bent. They bend around the edges of the barrier to fill in the spaces behind it. So as the waves are coming in, they're doing something like this. They're bending around the barrier. This is why you can hear around corners. This is why shadows are not perfectly sharp lines that go from dark to light gradually. It's the bending of the wave as it passes the edge. So reflection is bouncing. It hits the barrier, bounces off. Refraction and diffraction are bending. Refraction is bending as it goes through the surface into another medium. Diffraction is bending as it goes around the edge. Last thing I want to mention in this whirlwind tour of waves is the Doppler effect. It's a shift in frequency caused by a movement of the wave source. Whatever is producing the light, whatever is producing the sound is moving. If it's moving away from us, we are going to notice a lower frequency. It's going to stretch the waves out and produce a lower frequency sound, a lower pitch sound, or lower frequency light. The light will appear shifted towards red. If it's moving towards us, if it's getting closer, we'll get a higher frequency sound or a higher pitch sound, or we'll see higher frequency light if it's moving fast enough. In other words, it'll be shifted towards blue. Good illustrations of that right here. If a train is sitting still and it's blaring its horn, a person in front, a person in back will hear the exact same thing. If the train is moving, however, they're going to hear different sounds. The person in front is going to hear a higher pitched sound because the waves are squeezed together. The person behind will hear a lower pitched sound because the waves are being spread out. Same thing would happen with light. If the light is moving towards you, it would squeeze the waves together, and you would see a higher frequency light, in this case blue. If it's moving away from you, it's going to stretch the light out. You're going to see lower frequency light. Lower frequency light is red. It's called the red shift and the blue shift. It's actually the evidence we use to know that the universe is expanding. We can look at galaxies and see what their color is to know if they're moving away from us or towards us. That is it for our whirlwind tour of waves. Hope you enjoyed it. See you next time.